Hey all.
There we go. Is there anyone else we are waiting on right now?
You said Tim is unavailable right now, right?
Martin should
I-
confirm. Is he available? Is he not available, Martin?
I actually don't know, but I think my last stand is that he's not coming.
Yeah, I mean, he just flew back today, so I think it's reasonable to give him the day of that.
Yeah.
Either way of the recording.
He was only 45 minutes late for coffee today, so it was interesting. So I think he's still a bit exhausted.
Yeah,
Is he
he had-
jet lagged?
Oh, never mind. There's Tim.
Speak of the devil.
Answer is complete. Okie doke. Wait for Tim. Can you hear?
Yeah.
There we go. Okay, so I think just we'll probably start with also actually I'm just going to share my whole screen for a second. FYI, for folks who don't know, and I'm probably going to get it wrong, hypothetically, we have live updating Doxygen files. So you can see the docs that hypothetically exist. So if you go to like the class list and things, you can see like all of the like, you know, the type entry methods and, you know, there's actually some docs on the type analysis stuff. There are some docs in there are fewer, but still some docs on activity analysis, and increasingly few as you get the higher up analyses, basically, because you started writing docs and then slowly ran out of steam in certain places. But yeah, so I guess I will start at the base of all of the types, the base type. Yeah, so basically there's a couple of fundamental types here that we have. Integer is, as you would expect, it is, you know, an individual integer. Float, you know, is later separated into separate varieties of float that we'll see in a second, but generically representing a floating point type. Pointer, again, pointer. Anything is a special one, which means that it can be used as all of these three, and it is legal to be used as all of these three. Basically, it's a special placeholder for 0 in most cases, because if you have a 0 number, that could represent an integer, that could represent the null pointer, that could represent a 0 float, and thus it's like, for an individual number, it's very ambiguous what it actually represents. It can also be used in like certain other contexts as well. Unknown just means we have no information about it, and then you can do different sort of like unions. So if you have like a you know, type information of a pointer or an unknown would come out as a pointer, a float or an unknown would come out as float, etc. If you had where it sort of picks the most information sort of variant of the things, anything wins that, then followed by these guys, unknown loses all of those. You also have, and that's sort of like an or logical sense. You also have an and logical sense, where basically if two things are not compatible, it will become unknown, or if something is with unknown, and the point there is to guarantee. The example here is like, suppose you have like a chunk of memory, right? And you want to check that they're all something, you just, you know, and them all across. And if one of the locations was unknown, then it would just be unknown. Anyways, the base type is just a super simple enum. There are some fairly simple things here. We could potentially even add docs to describe what these things mean. Actually, there is something. Hey, look at that. Look at that. It's just not auto-docked for some reason. Anyways, there's technically docs. If someone wants to figure out how to make those docs appear on the Doxygen. Again, when I say we're going increasing levels of where there are docs. So this maintains the same sort of detail that I was talking about a second ago. Anyways, concrete type is basically a wrapper around a base type, where the only difference is now it knows which float. So again, this just knows that it is a float, versus here it actually has the individual float. We could at one point imagine sort of fusing these things together to represent, you know, like float 8, float 16, float 32, float whatever, but right now these are sort of separate, where it will sort of like, you know, use this to layer on top of, and it has a lot more sort of information and a lot of different helper functions, like, you know, is it an integer type? Could it be a pointer? Where again, could it be a pointer? If we look at the definition of this real quick, it's saying like, a pointer obviously could be a pointer, and anything could be used as a pointer, and unknown could be used as a pointer. And, same thing with like, is possible float, and you get the sort of gist of these types of things. Yeah, and then you got a bunch of these other helper methods, the or in and the checked or in sort of do the things that I was alluding to before. One actually uses the other. So we're going to take a look at or in for a second. Actually, no, I'll go the other way. We'll start at checked or in. And, as the docs that kind of exists says that, this is a current type. Set the current type, the logical, like type or of itself, and this concrete type, returning whether or not it's changed. The reason why the return whether or not it's changed is because, it could propagate information. So if this doesn't change anything, then you can stop the propagation. A lot of these types of flags also have this special variety pointer it's same, which basically says consider pointers or integers interchangeable from each other. This is often useful in practice because if you have something that's either a pointer or an integer, many rules will consider both of those things inactive or similar to each other. So if you have like a mem copy and you're copying pointer data, the same rule would apply as either a pointer or an integer. Whereas if it's a float, you need a different thing. So it allows you now to sort of like or in, like, again, that chunk of memory with the not caring whether it's a pointer or an integer. This other special flag here will be set to true or false, depending on or whether or not it was legal to do this. So there are certain types of ors that are logically permissible, like you have like something within an anything, or like something with an unknown, or two sort of varieties that are similar, like an int with an int. Also, you should feel free to just interrupt me at any point in time. But if you have like a float and an int, it will yell at you because like you cannot have something be a float and an int. So in this version of it, we'll just set this to saying illegal, versus this version of it will, yell at you depending on the result of it. It's depending on where you look inside of type analysis, it might use one versus the other. We're trying to get more of the things to use this one at the top here, so then we can have the assertion occur with a print as to which instruction caused the illegal merge, versus here, you don't know which one caused it, and having the context is easier to read. Does that all immediately make sense for the type union? Okay, cool. And does basically just the same thing that you would have expected and basically does the exact sort of thing that you'd expect, except now rather than logical or of pieces, logical and of things. So you need both of them to be floats to return. Versus here, if you had one float and one unknown, it would be still a float. So and versus or. And again, we have, special operator versions, and we have other variants. We also even have like this binop variety that attempts to do the rules for, yeah, we have this binop variety, which will attempt to do the binary operation. So if you have like an add or a subtract or whatever else, it has like many of these guys implemented here, but there's also some of it that is dependent on the value. So here, this assumes that you don't know the value, versus in the actual type analysis rule itself, it'll have some extra things on top of it that also assume the value to be able to look at some stuff. Yeah. And then, just some other helper things. Anything is weird, so sometimes might want to be removed. So this basically is a helper function, purge anything that just, if you have an anything, sets it to unknown. And comparison is necessary to be able to put it inside of a map. So we just define an ordering, where the ordering is just, if the enums compare as the first, and then the types compare, and then the enums compare. Type tree is, again, the main workhorse of this sort of stuff, which basically it has the listing of the individual offsets and then the actual concrete type. So those listing of offsets represent a pointer, or like levels of pointer indirection. So the gist here is, suppose you had an actual pointer, right? It would point to something. So we would want to represent both the outermost level as being a pointer, but also the fact that, like it's a pointer to an int. So here you might say that, like at offset, 0 is a pointer, and then offset 0, 0, it's an int, representing that fact that in that pointer at offset 0 it's an int, and so on. So right now it's implemented, unfortunately, using a literal std map of vectors to concrete types. There have been at various points some partial work to make this a happier thing using a trie, which would enable a lot of these operations to work faster. And we'll see why some of these operations are faster in this sort of like trie tree based version. So one of the most common operations here is this only function, which basically says, given an existing type tree, and I'll see if I can draw because drawing is fun. We're like given an existing type tree, and again, this is truly a tree, right? So you have, like at offset 0, it goes to, like 0 and 1 and 2, and then 0, 1, 2 might themselves go to things. Theoretical view, again, it's based off of a map. The point of this only is that we will, point to that. So you have like, at offset 3 as the thing there. In sort of the numeric terms of how this works right now, suppose you have a type tree of like, 0, 4, and you have a separate thing of 0 here. So this guy, first of all, some invariant you have to have is if you have something with a subsequent indices at that same prefix, it has to be a pointer, since you can't have an integer being also like stuff following it. So suppose this was like a pointer to an integer, right? This is what this would represent. And then we wanted to only it would then change this into a new type tree, where if we did like only with 3, then it would be 3, 0 pointer, and then 3, 0, 4. And again, to illustrate the previous thing that I said about the trees are good, current representation bad, if this was literally a tree, this would be a constant time operation. Since this is not a tree, it is an O of, all of the things need updating operation. And this is why trees are good. Anyways, sort of, you have other versions that do kind of operations which do the opposite. Also, do you mind if I erase the doodle that I did? Okay, I will now erase my doodles. So you have things that sort of do the opposite of that, where you have like this data 0, which picks off, at offset 0, the things that are inside of there, and offset, inner 0 is sort of like a version of data 0 that then also does a lookup at that individual location. The other thing that's also worth saying here is type trees right now have positive indices only, which means that you can only have a type tree that says like, at this offset here, it's something at offset 2 there, so 3, 0, whatever else. The one exception to that is we have a special -1 index, which basically means all locations this type applies. Where, like you have a -1 is an int, this means that for all locations inside of this register, it's an int. Or if you have like -1, it's a float, then like all locations in this register, it's a float. Yeah. Continuing on, you have, again, insert is the most time expensive sort of operation, and it's the real workhorse behind it. So basically, given a set of those indices in an actual concrete type, it will attempt to put it into the map, which you could think is, oh, that's easy, just do a map.insert. No, harder than that, because if you have any of these -1s, there might be accidental collisions, right? Where if like, if you have something at a -1, zeros and sort of thing, and you're inserting something with, a bunch of zeros, then the -1 index would sort of trump that. So you need to first sort of see if that you would need to union those things together. And the again, basic gist here is that it has special support for seeing if there's a collision on the specific to -1s and other sort of pieces. And then also if it needs to delete or other offsets for sake of performance, as alluded to earlier, because the type tree can get kind of long, it has specific, maximum offsets, with the exception of it will keep a, sorry, taking a step back. When I described the depth of that tree, or the number of those indices, we have this magical, like enzyme max type depth. So if you've ever seen that warning of like, greater than 6, warning, not inserting. It's because someone tried to insert something into a type tree at a greater depth. So someone like did an only of a fully depthed out sort of thing. And the reason that there's a finite depth here is because otherwise you can create an infinite depth thing and just continue on to infinity. This is bad. So for performance, you got to stop. Ideally, again, this is when it becomes a tree or like a partial cycle, then you can like point it to itself and then not have like an infinite recursion on itself in terms of memory space. But anyways, it has some individual sort of like internal mappings of like, what are the max depths at any locations. There is a specific, and similarly, there's also a max offset. So, we have these sets of indices, which, include -1, but then all 0 or positive integers. But there's still a max of that, because if not, you could have, like theoretically infinite number of things, and that's as a guaranteed state space really, really big. So sort of the point of having both a max depth and a max offset means, in theory, there is a guaranteed fixed point where this will finish all of the updates. And that max, I think, is usually defaultly set to like 500 or 512 or whatever else. Anyways, so the point of some of these extra sort of internal mappings is done to specify the fact that, how close are we to any of these max pieces? Because there is one special case wherein if you have only one thing inside of your tree, even if it's bigger than the max offsets, we'll keep it. Because if it's just one, then we would always lose that information, and we still would want to keep that information, and the point of that maximum is to prevent sort of like an infinite time being spent. But if there's only one thing, it will never be infinite. There's still a limit there, which is the at most one sort of thing. So if you insert something at a smaller depth to something that is already beyond this limit, then it will kick out the larger depth one to, again, sort of maintain this this property. Yeah, so past the sort of technical internals of it, you have a lot of these special helper functions, which are from the user of this class sort of point of view. Only is fairly common. Just int is what you would expect. It prunes off everything that is not an int. Inner zero sort of, or data zero sort of like goes into the tree, whereas like only goes out of the tree, except data zero does it specifically at 0, and only is nice. It lets you pick the other direction. This is just a slightly optimized version of data zero, then pick the version there. So you can always do a lookup at any individual location that you care about, and then the location finder is equivalent to like the map lookup with some, again, special case handling for -1s, because if you look for a -1, then it'll, it would still apply even if you had it at 0. So if you had a type tree that says, at index -1, it's a float, and you asked for what is the value at 4, then you would still want it to return float, because -1 means it is everywhere, versus if you just did like a map index lookup, it would return, oh, I don't have anything there. So equivalent to unknown. And yeah, any place that there's not a defined operation inside of, that's equivalent to unknown. Going on, clear, given a range of offsets, it'll remove any mappings in the range start through end. Yeah, or etc. Lookup is sort of it'll offset into it in a different way, whereas the data zero only looked at the 0. And this is sort of like the equivalent of like a pointer lookup. So if we look at that, it says pick all the submappings whose first index is in the range 0 through len and remove the first index. Again, it's a pseudo inverse of the only operation. Canonicalize in place. Given the fact that this represents a type tree, try to make it as concise as possible. And the basic gist here is like by providing it a length, this allows us to upgrade things to -1. Right, so if you have something that's like int 1, 2, 3, 4, and we know that this register is only a register of size 4, then this canonicalize in place will say, oh, great, I can just replace it with a -1, and thus canonicalizing it, which makes it easier to represent and all those good things. Keep -1 is, keep only pointers, or anything represented by the repeated -1 value. Check if it's all floats. Schiff indices is one of the other big workhorses here, whereas this sort of name implies like given, indices given all of the indices, replace those with a new offset. So like, prefix them all with offset, and also limit the total maximum. So if you had, this is now not a tree sense, it really only applies to the outermost level. And this is why most of these operations sort of like to do modifications on the top level, either adding a level or removing a level. And that's also, again, why the tree stuff is nice. But let's imagine we had like an index space here. So if we had stuff at some initial offset here, and they go to some max size. So some offset plus size. It'll shift all of these guys to wherever this new add offset is. So if add offset is here, it'll move them all down that direction, which is useful if you have like a get element pointer and you like offset stuff, or otherwise you like add to a pointer and like, it's the equivalent of like just move, basically. Sorry, annotate, gotta go clear. Yep. Extra sort of variations like, replace all minuses with zeros or ints with anythings and keep just the anythings, remove all the anythings. You have the same versions of your ors ins, where now you can take, either a type tree to or in together, and it'll do all the rules to fuse all the indices and so on and so forth, going up the tree. Does the data structures of type analysis and stuff make sense, or any questions on that? Also, if there's something that you prefer I go into depth about as opposed to the specifics of things, let me know, and I will focus more on those instead of just going to ramble going all the way up the tree. Okay, cool. We can now go inside of type analysis itself. So the actual analysis is inside of a thing called type analyzer. So type analysis as an analysis is pretty tame. You just basically say go analyze a function given the argument types and the return types, where technically it's not just the types but also the known values of said arguments, and obviously the individual function itself. So this function type info is the set of information you need to be able to query it. If you look at the analyze function, what actually happens inside of here is, it first checks if we've already analyzed this. So type analysis is literally just the equivalent of like a map of these function type infos to analysis states. And the reason is because, type analyzing one function might require you to analyze a different function, but specifically the variations there might differ. So if you have a function which is add, and like it added a value which represented a pointer, you get a different thing if that you added to a value that represented an integer, and so on. So it's mapped by both the function you're analyzing as well as the, again, starting states, so to speak. And then it goes, and analyzes it. And if we actually look at the analyzer, that's where all the meat is done. So basically, it just has rules for almost all the LLVM instructions and special rules for all the functions. You can think of this as similar to like the adjoint generator. There are some special variations of these, like there's one run phi hypotheses, because you could like not deduce certain pieces of information because there's a recurrence relations here, and this just adds special support for doing a recurrence relation. You'll also have like, sub-analyses that these things will go on and run. Mainly the types of things that you do here is let's do a go visit Bitcast as an example. There's two directions, up and down. And if you're going up, you're going to propagate the type results from the result up to its operands, and down does the opposite direction, where it takes from the operands to the end result. So for instance, the bitcast rule is really simple. Just directly propagate the input to the output and the output to the input, since the cast won't change the type of the underlying data. You tell it to do so using this update analysis function. This is the thing I want to update. This is the new type tree that I want it to become. And then this is which, rule is causing the update. So again, the two big methods are update analysis, which you'll call and will cause the update, and get analysis, which you can query any analysis type state, which will return a type tree for any operation or for any value that you can see. Update analysis as the definition is a bit special, because this is where, if you've heard me talk about, why doesn't it give me the line number? Darn. Anyways, if you've heard me talk about the unions sort of stuff, this is where it fixes the handling of unions. So if we were to just run this always, then it would have to assume that if you always do the update when given an update from the individual instruction, then it assumes that that type is always true across all time, across all code paths. So if you had a union where on one code path it was an int and one code path it's a float, you'd eventually get a collision, because the float path would say, go update my operand there as being a float, and the int one would say, go update that one as being an int, and it would yell at you. So that is actually the default behavior, where it assumes strict aliasing, and thus it can do this. If you want to have less good type information but support unions, then you have to turn the enzyme strict aliasing flag equal to false, where it will only do that update if it sort of like strictly, or I'm going to get the term wrong, but if it post dominates it. So it's guaranteed to always, get to that point and execute it. So that's why if you see this, like, if not strict aliasing, then, check for the corresponding dominance relation and skip it, if it doesn't have the dominating sort of stuff. And then it will literally just do a, like or in with the previous analysis state of the map with the one that you're adding into it, and will yell at you with an illegal type analysis if it's not legal to OR those guys in together. There is an extra special function here, get constant analysis, which will do what you would expect, except now just for constants. If you're doing MLIR stuff, this won't matter, because constants are operands, so you won't need a special one. The reason it's special here is just because, like, you don't want to have to like reanalyze every single constant for all of the individual sub function states. You want to have ones where they're all there. Yeah, and then you have rules for basically all the types of things that you want to do. The most tricky one is the get element pointer rule, so I showed you like one of the easier ones. So the get element pointer rule basically is first of all, if you have an undef pointer, so this can look at both the instructions, its values, and everything about it, right? So if you're gepping an undef value, then just tell it to be an anything, because anything is sort of tantamount equivalent to like an undef or a zero or whatever else. That's only what it should be used for. And then there's some special handling on if it's inbounds, then we know it's a pointer under certain conditions, since inbounds has specific semantics. Otherwise, it may not even be a pointer, right? Because you could use get element pointer on an int to pointer to just do like addition math and then get the result of that, and then pointer to int it. People can do terrible things with LLVM, and that's why this is like very, very like get all the things happy. Ironically, the MLIR side, you can make some probably nicer assumptions, but here we're very conservative. And then the thing that we do here is for all the GEP indices, we will go and do the offsets. The difference is, for some of your GEP indices, if they're all constants, great, compute the total offset and then shift the value using that shifter that we talked about earlier. But sometimes, you might have a GEP with an array offset that's not a constant inside of it, and then it's sort of like, how much should you actually move it? And that's unclear. So this is also why type analysis keeps track of the constant integer values that are guaranteed to be run. So if you have like a constant integer, 0 plus 1 even as an instruction level, then we will do the analysis to say, oh, that's equivalent to just 1. And similarly, it will go through functions that way. The other thing that this will do is for loops, we will be able to say, oh, if your loop has known bounds, then we know that this value, like the integer of the iteration space of the loop, is guaranteed to be 0 and 1 and 2 and 3 all the way up to the constant loop bound size, because we know it has to run all of those iterations. So we can then also go and run all of the constant loop bounds that we see, and then put all of those types in at once, which is really useful, because otherwise we have none of those types. And that's basically what this sort of thing does. It looks at all of the pieces, and it tries to consider what the corresponding known integral values are for all of the offsets, and inserts them into this sort of like vector of sets, where the index of this vector is like, the first offset to the gap, and then all the values that first offset could be, and the second offset to the gap, and then all of the values that it could be, and so on and so forth. And then it computes that, and then runs all of the the shift indices for all of the the pointer offsets, and then ors them in going up, ors them in going down, and then finally just does the update. So this is the most complicated rule by far, and that's how that works. Most of them are pretty easy, where it's just like FP trunk is like great. So that is the types of the truncation are like the input and the output floating point truncation, are like any constant special functions that you might have, like might have an MPI whatever function. You just say, oh, it's a pointer there, it's a pointer there, it's a whatever else there, and we similarly have a bunch of type rules here for functions that are interesting that we know types of. So then that can seed all the analyses. Any questions otherwise about type analysis?
William, I just had a quick question on, it was line
Yeah.
1469 and 1470.
Yeah.
It was just, I might have missed a bit. It was just, I was curious about like why we did both of them operations in one after the other one. Just, I was trying to get the subtlety when you were talking through it, and I think maybe I missed it or whatever.
Yeah, give me a second.
Sorry to put you on the spot. Yeah.
Yeah, okay, so this basically is a if you know that a pointer is always pointing for all offsets to a float, we want to keep, even if you offset or you gap into that float, then we want to preserve that. So that's the equivalent of the keep -1
Right.
sort of bit of it right here. And then the pointer analysis stuff is even independent of that. If at the outermost level it is a pointer, hence it'll just look at the insides of it and then do the -1. So this is sort of like is it a pointer? And then this part is like, what are the values inside the pointer? To be clear, I'm reading it fast, and I could get this wrong, but I think that's what these two.
All right. Yeah. No, thanks a lot for that.
Definitely something we should go add docs for. Inside right here.
I do have another question for type analysis, since I noticed one of my use cases went from like
Also,
6 hours to a few minutes.
I'm at 1% battery. I'm gonna plug in real fast. If I disappear, I will return. Yeah, sorry, continue to talk, but I may end up dropping out because power.
Yeah, so I noticed it got like 90 times faster by moving to Rust. And the one difference we have is that we initialize type analysis based on the type information which we have from the Rust compiler. But the thing is, I start like the outer function which I differentiate effectively has, yeah, okay. Yeah, so effectively I was wondering how type information is propagated across function calls. Like if I seed it for the outermost function and then I create some arrays out of it, how much analysis is going to run and how much it's just going to reuse that information, because we said a lot of -1s or so in the outer levels for arrays and vectors.
So the intuition for the minus ones, primarily that they're used for arrays and vectors, and that's why they're propagated.
Mhm. Yeah. Yeah, I mean, I'm just wondering because based on like an input array, I create some new arrays of different sizes. So like, since it takes the type from the -1, I hope that it also recognizes directly that the new vector is going to be like -1 of that float type everywhere, instead of looking specifically at every single place. Because depending on that, like if I start nesting more function calls, or it becomes increasingly slow, like if I analyze every new array. And the difference was huge, like 90 times faster if we see the outer values.
Hi, sorry.
Hey.
My computer
Yes.
obviously died, so I didn't hear basically anything that you said. Can
Sure.
you repeat that?
Of course. Yes, so I noticed that since we for Rust initialized a lot of type information on the outermost level, like with -1s for vectors and arrays, it got a huge amount faster, like 9 times faster. Now I wonder, based on those -1s, how are they propagated by basically in like the down direction if we have if we create a new array and pass the new array to an inner function, which then by the chain rule is also going to get differentiated? Is it like looking at the -1 and directly moves over the -1 to the new array being created, even though they might have different length and there's a bit of math in between? Is it like analyzing every single entry of the new array being created? Because Enzyme by itself can have like different activity for each array entry. Because depending on the answer, like on the Rust side, we might become really slow once people start creating more arrays, the nesting functions deeper, or we just going to stay fast if we have the information from the outer side.
So basically the gist is like it won't store like you should look at the store rule, I think is basically the way to answer your question. Like it will avoid storing a -1 since it's unclear whether or not you'd store like a pointer that has like this necessarily always in certain circumstances. There are other circumstances that you can. However, this is sort of similar to like what one of the Julia level we do, which is we define a custom type rule, which you can also define custom type rules too, for like an array allocation of a type to just initialize it as -1, that type always. So then you know the correct properties. I'm not sure that answered your question, so I think I need you to tell me what parts that I didn't answer. So
yeah, so I mean, I know if I got it right from the Julia side, like if you have nested function calls and call another function at an earlier level, you look like at these inner functions and already save the type information for Enzyme to pick it up later, right? Based on your specific rules.
I'm gonna give you the screen share real fast, and I'll let you draw some example code. I think that might be the most useful.
Give me a second. Share screen. Yes. I think you should be able to see it.
Okay, yeah.
Yeah, exactly. So this one is like some C++ example where the outer, oh no, wait, I think it's Rust. Yeah, so basically we initialize our input array here. And so we know, well, all of these are float values. Now, based on these, I pass the array to a new function, create a new vector, like distances in that case. Then I adjust the distances a bit. And now I pass the distances to the actual function doing the hard work, so polynomials. And this all got a lot faster. So I assume initializing the input arrays already kind of initializes the distances in an efficient way. And
so it will propagate the information interprocedurally. So if you have something that like returns the same array as an example, and that same array is a -1, then it will propagate that out. I guess another quick thing that I'm going to add, sorry for the interruption, is Enzyme will also run these analyses interprocedurally. So then the first it'll do all the things it can in the current function. And then once it finishes that up, it'll do all of the interprocedural analyses, which will set up with the current state it knows of each call's inputs and outputs. and then use that to see if it changes any of the inputs or outputs, and then, go back, run all the internal things, and continue to do that until it hits a fixed point of being happy. It also seeds many of these analyses with any information that it can. So if there's custom type rules, that can seed analyses. Any TBAA will seed analyses, where the TBAA basically just says for this load or this store, like I know this information always. It's just like an extra way of injecting information. Anyway, sorry, continue.
Yeah, no, that's fine. It does sound a bit like on the Rust side, like we can improve it further, but it should already do reasonably well, even if we start nesting functions deeper. That was kind of what I was hoping for. Okay.
Nice.
Yeah, thanks.
Other type analysis, questions, shenanigan, etc.
Real quick, by offset into this data structure, do you specifically mean byte offset?
Yes.
Can you
Or
have
potentially,
can you have like invalid cases where you somehow point to the middle of, say, a 32-bit float, and the information just like no longer makes sense to be interpreted as a float?
Yeah, so that would be the float sort of thing is a little bit special, where you don't say float as so integers, you just put like integer at every single byte offset where it's an integer. If you have like a 32-bit float, then it would like every 4 bytes be a float. So like 0 float, 4 colon float, 8 colon float. So then if you look it up at like byte offset 1, it would be an unknown, or byte offset 2 would be an unknown, 3 would be an unknown. If you had like the -1 float, that if you were to do the sort of shift offset mechanism, which could force a length, changing a -1 now into 0, 4, 8 for whatever your length is. And that's also one of the other uses of this shift offset sort of magic function, is to enforce lengths and to force infinite length sequences into the finite length ones. It will only do so at the corresponding like byte size of the float.
Right. So you might end up at the case where you're explicitly enumerating the 0, 4, 8 up to however long.
Yes.
Got you.
Yeah. And then if you try to query it at a different point, then it would return like unknown, as an example.
Cool. Thanks.
Yeah.
Okay. One more question, which I just got about the TA. How well separated is this? Because I was wondering, from like those 4 minutes of compile time, which are basically like almost all of Enzyme. I mean, the Rust compiler itself is pretty fast in comparison. How can I find out like where Enzyme is spending their time? Like if the TA is reasonably separated, I might, like in the most simple case, have a global variable like a global float or so, and I can just add the time. Like once we start with TA, I like take the current time. Once we leave it, I take the current time and add the difference to our global. And at the end of Enzyme, I can just print, hey, we spent so much time in TA. Like, would that work? Or like, what would be a good place if I were interested in measuring that?
Yeah, so I'd probably put like a timer around the type analysis itself, like not in type analyzer, because it will recur on itself, but on the thing that calls it. Speaking of which, a couple of things that I'll add here, which again, current data structures and setups mean that it's going to be much more slow than other sort of things. So if you have recursive data structures, or just data structures of high depth, that's what, and the reason why this is slow is, imagine you had like a binary tree, right? So you have like, pointer and then tree, pointer, tree, maybe even a size. Let me just take the screen share for a second, and I can draw. So, right, we would have, so here at, like offset 0, we would have our object, and then we'd have our other object, and then each one of those would have their own objects, right? And it would gradually fill the whole thing until it eventually hit a depth limit, where that depth limit, again, by default is 6. And you can see why then this is a potential like 2 to the 6th or 2 to the depth number of, offsets inside of it. Hence the current way of representing it means that recursive data structures or other sort of things are very, very heavy in terms of the load that Enzyme would have for being able to like represent it in this form. This is also sort of why at one point, in addition to the type tree becoming a trie sort of thing, there's also some amount of trying to make it enabled from shared, so it could actually point to itself. So then rather than having, each one of these guys be a new offset, it could be like, oh, it's equivalent to pointing to there. And then like I could still represent how it goes all the way down, but then not do so in such a way that requires infinite data to be able to store the things. Because also infinite data means, like the first round of fixed point updates will add this level, and the second round of fixed point updates add this level, the third round of fixed point updates, and you see how that also takes way more time for total number of levels, versus if you just had it there, it's like, oh great, you have the theoretical infinite length thing just instantly represented. Once again, why tree form is good, and that's why I sort of say the shared from bit would be like the second follow-up to being trie-like rather than the map-like. But yeah, anyways, there's that. That also is a good way to explain where and why certain performance things could happen. You can also just seed it saying not to do other pieces. But yes, for the comments, or an oct tree, or in other things. And to be clear, it perfectly goes and handles. That's why we have like linked list tests and all the other things. But those are the types of data structure which would make it the innermost operation cry the most. And if every innermost operation is doing this, then it'd be like that number of times offset to however many things is happening. But yeah. Any other type analysis question to shenanigans or other things? Does that mean we're ready for activity analysis? Which I will say, we already have a mostly functioning implementation of this in MLIR as well, by the way, landed in Enzyme itself, which we need to fuse with the LLVM one, which it forked itself from, because having two implementations is bad, especially when one receives updates and the other does not. Yeah, so let's go to just the LLVM activity analysis, and then I can basically just explain how the MLIR one is basically the same, except changing the use and other API key stuff. So activity analyzer is similar in that it has an up-down sort of notion like we had inside of the type analyzer. It actually does a couple more things in depth with hypotheses. So the core key functions here that are the workhorses for everything is is constant value and is constant instruction. And you can have operations which are the whole quadrant of these things. And let's actually talk really quickly about what examples of those would be. So here I'm going to put instructions on this axis. I'm going to put values on this axis. And then here we're going to do active, constant, constant, active. So we're going to play this as an interactive game. Can anyone give me an example of something that's both a constant instruction and a constant value? I'll start off the game here for a second. So imagine we have some value, %v equals, add, 2, 1. So this is clearly a constant value because it's an integer, and we presume that all integers are constant values. We can also in the future, speaking back to type analysis, add an extra version of active integer inside of our type analysis, which we should at one point, but we don't have that right now. Anyways, because it's an integer, we know that it's a constant value since integers cannot store themselves any active data, and it's also a constant instruction because the add itself doesn't propagate any derivative information. So both constant instruction, constant value. Anyone got ideas for any of the other 3 quadrant examples?
To be clear,
Liam, oh yeah.
this is a question I had from a while ago, but on this notion of constant instruction versus constant value, by propagating derivative information, do you mean specifically as a side effect?
Either as a side effect or from the operands to the result.
So do both count? If so,
Both
does that
count
mean if you end up creating an active result, then you have propagated derivative information?
Yes.
Okay, I have further questions about the semantic of some of the activity analysis tests then, but
Yes. But before then, let's still play the game. Ideas of, anything else in this quadrant. Like, what is an example of something that's an active instruction and an active value?
F multiply on 2 float variables.
Exactly. That is a great example. So we have, percent E here equals, F mol of, I'm just going to do A and itself because I can't draw. Where again, the result here is active because we know that, this multiply of 2 active variables is also going to be active in this given context, and it propagates the information into it. Therefore, it is an active instruction. So both active instruction and active value. Great. What about the other quadrants? How about? Oh, yeah.
I think constant value active instruction should be like a compare.
What do you mean by compare exactly?
Like compare and then unsigned or like a less than.
So you're saying if you had like A is less than B.
Yeah.
So I agree with you that this is going to be a constant value. I disagree, this is not a constant instruction, or this is not an active instruction, it's a constant instruction, because this less than comparison doesn't propagate information, because it neither as a side effect, moves some derivative information from one location to another, nor does it as a return by moving some derivative information into the result. And that's sort of like the 2 ways that propagation can occur. So this guy would instead be over here. So constant value and constant instruction. If that makes sense.
so then in that quadrant, would a store fit there?
A store would fit there, yes. So you can have, star, and again, I'm using C syntax rather than LVM syntax here for example, pointer equals V, because the result of a store is void, but this actually moves derivative information, in this case, into the pointer. However, again, it only does so if the thing that it's storing is active. If the thing that it was storing was constant, it would not. But otherwise, perfect example. Any other sort of examples? I'll give you a hint. You can put stores in things, like functions.
Memset.
I might say memcopy rather than memset, because memset usually is like setting with a bunch of zeros, but I'll give you memcopy. But yeah, okay, now we have the trickiest quadrant. Active value, constant instruction. Alternatively, you can tell me and try to prove that something cannot exist, or give me an example. To be clear, you could have done that for either of the previous boxes, but since we do have an example, I think trying to prove that one doesn't exist would be a harder task.
This does go back to my previous question, though, when I asked if creation or the result being active implies that an instruction has propagated a derivative signal. So
Yeah, go on.
I suspect that there are examples of this quadrant because I think you said that before, but does that not contradict what you answered with my question?
No, let me just give an example here that might explain. Basically, this type of quadrant, I would need to think more to say so definitively, but at first glance, I can only think of examples that involve pointers. And the reason why is like, you can have operations on pointers that, if you have an input pointer or an output pointer, that could point to active data. But doing math on the pointer itself doesn't move active data around. It just changes what you're pointing at. Right? So as an example, if you have some active pointer and you add 1 to it, like you offset it and like by 1, this guy, the result of it, right, is going to still be an active pointer, but adding 1 to a pointer doesn't change the inside data. It just points you to a different location. So like a gep is an example of one of these. A bitcast of a pointer is an example of this. Even more generalizing, an example could be malloc, and this is the harder bit, right? Because malloc clearly takes no active arguments, does no ability to transfer things, but its result definitely, and this is where it's contextually dependent on the rest of the surroundings, active. And this is also sort of why its activity isn't a individual property, but it's a proof of data flow. So this is sort of then the next sort of bit that I think is worth talking about here. So if you have like an instruction, you have some f of x, right? A equals, x squared, b equals, a plus x, c equals a times a, return c. What is the most, aggressive as opposed to conservative type analysis of this? And we're going to make the 2 columns here. We have instruction and value. And I'm going to tell you for a fact that, the input here is an active value, and the return itself, it's returning an active value, because we always see the analyses with the input and the results, right? Whenever we call autodiff, you might not see it depending on which of the languages, it might automatically deduce for you, but it is. Yeah, so how should we fill this out? And I'm just going to say that the return instruction itself, we're not going to care about it. So I'm going to just mark that as an X. Well, since we're returning an active value, right? The whole point about activity analysis is proving whether or not there is a path from an active input to an active output. Where here, again, active input or output is even like too specific. We don't actually care about that, but just a path where active data can flow. So, here we can see that C could have come from, or this return value comes from C itself comes from A itself comes from X. So there is a path. This is the path. So therefore, this value that's being returned here, again, like we're ignoring this because a return doesn't return a value, whatever. Anyways, so this C here is indeed a active value. This A here is an active value. All good. Squaring something means it's an active instruction, times something it means it's an active instruction. But you'll also notice I explicitly didn't talk about B. And that's because in a super aggressive version of the world, it is not active because it's never used. So it cannot propagate all the way through. Right? Even though it is the sum of two things. If you were to use B, then and like return B, it would become active. Great. And similarly here, if instead of returning C, I returned like, the number 7, right? The number 7 is a constant. It is not active by definition. Now, even though we're returning it, like it hits that point where the cycle of where the information flow stops is. And the same thing, and this is an easier version because we talked about registers, also applies to memory, right? Where you could allocate memory on its own. So you have some like double array. And it depends how you use that memory to be able to determine whether or not it's active. If you just store, inactive things inside of it, great, it's inactive. If you store active data inside of it, then it could still be inactive if it's never loaded from. So you need to both have a path of a load and a store potential for the pointer. The pointer is even more tricky because if you return the load could be later or the store could have been earlier. Whereas the register one is a little bit easier because you can always follow the path. Of course, in a real function, you have both registers and pointers, so you need both of these things to combine together. And that's actually why if we look at the definitions of these guys, value has a lot of easy things. Instruction has also a lot of easy things, but value also has it could be a pointer, also check for a bunch of other things too, because there's more potential paths that exist to be able to transfer derivative information, where now path is through memory in addition to through data flow. This is kind of tricky, but hopefully that also makes sense.
Just to be sure, a load is an active instruction and an active value, right?
Again, if a path exists and the pointer itself is active.
Yeah, of course.
Yes. But yes. Oh no, sorry. And also the return result is not a pointer. If the return result is a pointer, then it is not an active value. So if you had like a, X equals, load of a double star star. And again, forgive my inability to draw clearly, is degrading. A very poorly written load of double star star. The result here would be an active value, but the instruction would not be an active instruction in this case, because this doesn't propagate derivative, information, but this pointer, contains something that contains, etc., derivative information, if that makes sense.
Yeah.
You can see why there are many interesting things, both in terms of bugs and activity analysis, and also we are insufficiently aggressive that can also come up. Any activity analysis design or like theory questions before we start talking about the insights a little bit? No questions? Everyone understands activity analysis 100% in theory? So thumbs up. Okay, feel free to interrupt me. Can I kill the drawings I made on the screen? Okay, cool. So let's actually go inside these beasts. Yeah, so we'll start with is constant value. So first, this contains some maps that are pre-populated potentially of existing constant values, existing active values, existing constant instructions, existing active instructions. Because if you know something, great, remember it for later. And as we can see here, if we already have proven this individual value to be constant, great, it's constant. If we've already proven it to be active, great, it's not constant. If a value is in neither of these maps, it could be either way. So the only states are it's in one and only one, or in neither, in which point it is unknown. And then we start off here with some special handling for constants and other sort of shenanigans. We have our magical known inactive stuff, which technically right now the way that's written, and there is a PR that starts to rewrite it, but I should finish cleaning it up. This stuff will actually have it be both active return and active instruction. There are some functions that might need to be only one or the other. Hence the other previous comment about like, if you're adding something here, you should know it's both, which basically means it cannot allocate memory. That could be used in an active way. So if it's a string, great, it's perfectly fine. If it's a malloc, be forewarned. Moving on, again, arguments, we should always have pre-populated. Globals, we can skip over a bit, but does some special looks and or yells at things. Again, constants. Calls, we have some special intrinsics to be able to explicitly mark either active or inactive, and we will listen to someone if they tell us as such. Then the sort of thing that we try to do is, because we talked earlier about paths of activity, the way that the analysis works, and to be clear, there are potentially better analyses or better ways to implement this. It's just the way it's implemented right now. So if anyone wants to improve it and be a better theoretically sound thing, always more than welcome. But basically what we try to do is we make a sub-activity analysis that's populated with the current state and hypothesize that it's either active or not. And under that assumption, can we prove that it is active or not, is basically how this analysis works for most of the types of things. And as I also mentioned, we have the special contains pointer bit, which we're going to skip over to begin with, and then we're going to get back to pointer land, because as I mentioned, pointers are hard. We'll come back to it in a second. Skipping lots of fun pointer stuff. Don't need to talk about pointers yet. We'll get to pointers later. Great. Now that we're past our pointers, now we can look at things that are guaranteed to be not pointers, that all we need to do is prove that activity either doesn't flow in or that it doesn't flow out. And thus this cuts off the flow, guaranteeing us that, it cannot flow through memory because this is not a pointer. Phi nodes are done as sort of like a special case in all of these checks, basically because if the directions equals 3 means both up and down. And the reason we have this is because if you have an assumption made and then you flow up, I'll actually draw this because this is visually useful. So suppose that you have a function f, right? And we talked about the register data flow thing here. So we have, x, you have, x becomes y somehow from x, y becomes z, b uses x, and we return z. This is a very similar case to what we talked about earlier, right? Basically, we're trying to do the case of like, okay, if we're going down, we can hypothesize that this guy is, inactive, and it's inactive going down if it has no uses of itself. Great, so then we try to see and hypothesize that this guy is inactive. We keep going down. We try to hypothesize that its user here is inactive. It's like, oh, nope, that was not inactive, bad. So we have to go, counter up saying, nope, your hypothesis was wrong. Nope, your hypothesis is wrong. And then it falls back saying, okay, well, I guess I'll assume it is active then, and then, continue the the levels of analyses, and so on and so forth. The reason why this direction exists is because we want to avoid having accidentally both up and down at the same time. So you could imagine a funky scenario where we assume this guy here is inactive because we're going down. And then suppose that this is inside of a loop, because this sort of thing would probably only occur inside of a loop, because otherwise it would be hard to go to a user that previously saw itself. And then suppose that right here, this guy was assumed to be inactive going up. Great, we've accidentally just hypothesized the stop between the return and here, and therefore we accidentally made something inactive for completely false reasons. So that's why if you're looking down, you're only allowed to do proofs based off of the users. And if you're looking up, you're only allowed to use proofs based off of the values, because if not, you could accidentally do a double-sided proof hypothesis where you assumed both the input was inactive and the output was inactive, and that just means you're going to get a wrong answer. So that's why there's the up-down bits. The caveat here on the phi node stuff basically is for performance reasons, if you already are in a so we'll take an analysis and then we'll basically fork it. So suppose we have an analysis which is up down. So it's both up and down. And right here, say we're going up, right? We'll fork it into an up analysis. And then the next time that we do something, we could fork it again into another up analysis. And then the next time we do something else, we could fork it again into another up analysis. And then, we would do the update, we remove it, we do the update, we remove it, we do the update, we remove it. And this is a bunch of unnecessary computation and allocation. So the basic gist is, can we reuse the hypothesis in certain cases? And the basic gist is, as long as you're not a recurrence, which can only happen on a phi node here. In the MLR sense, this would be on a block argument, where you could have a recurrence on the same value. Then we can reuse this guy since it won't impact the other computations. And this is also why, again, you see this if directions and up, so it's either up, down, or up, then in the special case that it's already, subset into an up, and we're not doing the recurrence here, then just reuse it. So we just do all the updates in place as opposed to doing another fork off of it. Yeah. And then otherwise it will, as you see here, make a new analysis activity analyzer that initializes it with the current state, sets it equal to up, and thus this is the fork. The other thing that activity analysis does is, if we can prove it, and I'm going to erase here for a second. The way that this works is, if we can prove that in this case it is an inactive instruction from its origin, meaning that none of the operands are used in an active way, and this is the cutting off from the top sort of thing, then great, we'll insert it as a known constant value. But someone in the future might be able to prove with a bright idea that this guy is actually potentially constant, but we just didn't know that yet. So then we'll add to this map here saying reevaluate this guy if we later prove that one of its operands is constant, because that could then change this guy's result. So that's what these maps are, as just say, go and serve these as potential reevaluation if the state of that would have potentially changed the activity state. Yeah, so we've got the up variety right here. We've got the down variety right here, where it's inactive from origin, inactive from users. Can I erase the drawing that I have right now? Cool. We can take a look at some of these guys. So inactive from users is kind of what you would expect, where we look at all the users. Some instructions just are definitionally inactive, and we have that sort of listed here. And then otherwise, we'll go through all the propagations, and we have stores. We're going to ignore the memory bits here for a second. But basically, if it keeps on going down and eventually isn't used in a thing, or used in a thing that's used in a thing, and so on and so forth, great. There we go. Going the opposite direction is inactive from origin. Right. looks at all the operands, and all of these also have special cases for functions, because some functions you might have, like some operands would cause it to be used similar to any instruction. Like if you have a offset into a pointer, changing the pointer itself being active or not will change whether or not the result is active, but changing the integer, it's always an integer. That will never cause it to be active if you're using it as an offset into an array, right? Yeah, this is also where some of the type analysis comes in, because if you can prove that something is an integer, great, it's not active because it's an integer. And similarly, if you can prove that a function returns only an integer, or rather does not have the ability to return a float, so just is not possibly returning a float. That's why we had some of those fancy type analysis, helper functions could be returning a float, and it only reads memory. It has to be inactive because it cannot flow memory. It cannot flow active data into memory since it's not storing anything. And it cannot flow it into the output since it's not returning any float. Therefore, all functions or all instructions with that behavior where it returns not float and does not write cannot possibly be active. And we hence generalization of all these sort of type rules and other shenanigans. Yeah, so then similarly, you have the pointer bit. The pointer bit is the most tricky part, in my opinion, of this, and why it's the most annoying. Or basically, if it contains a pointer, which first we use this lovely type analysis to say, do we need to think of it as a pointer? Do we really? And then be sad when we have to. This is, again, why anything that tells us it's not a pointer is a great type analysis result. And then basically the gist here is there's several different ways that it could matter. First of all, if this pointer is itself an offset into a different pointer, we should consider the base pointer as the sort of like origin, if we can. Sometimes we can't. This allows us to often get in the actual allocation of the entire block of memory rather than like an individual sort of offset into it, which lets us to do better analyses. Certain things where if we know this is, an offset of a constant pointer, it's a constant pointer. If we know it's an offset of an active pointer, it's an active pointer, etc. Then of course, we might not know where it comes from, either because it's an allocation or because it comes from the ether of who knows what's happening. Allocation functions actually have some special handling because we know that it wasn't created with active memory inside of it. You can have like a copy operation, right, that takes some active memory, or like a fill operation, which returns you a new pointer and then sets all the locations in. Allocation functions are special because we knew that they haven't started with any active memory inside of it. They just could be stored into at some point in the future. So we use that a bit for some more aggressive analyses. And we also have a special case for copy because we can. Anyways, the thing that we do here, and this is sort of the tricky bit, is we have an is value inactive from users, where that also has a bunch of special cases where we have this special use activity. So it looks at all these specific types of users. So if we can prove that, like, in an allocation, all of the loads or captures which could then load, which yada yada yada, you get the point there. If there is no potential load of a pointer, great, cannot flow memory through it, or if there is no potential active load of a pointer. Same thing with stores. Those stores are tricky, as discussed here, because you can store a pointer into another pointer. And what I mean by that is, suppose you have something, and I'm going to use text now for ease. Suppose you have something like this, double star star equals, alka. Right? Then we have double star data equals, malloc or something. You could potentially only store, so store, data x equals data. And then you could think, oh, this only is stored into this X. So then, if it's only stored into, it cannot contain active data since it has to flow, both a load and a store. But this inner pointer, right, data of 0 could equal active. And then you could load data 0. So it still could flow active data if the inner pointer inside of it, which is why the technical thing here is only non-pointer stores. In other words, if it actually is just float things, then the store cutoff as not active applies. But if it could store a pointer, then you could still have the scenario where it contains flowable data. Use activity none, contrary to its poor name, means look at all the uses of it. Use activity all stores means if there is no store into it at all, active or not, then it cannot possibly be active data. Because if you have a pointer that is never stored into, it's just undefined memory for all time. And therefore it's inactive. You'd be surprised how often that comes up for some reason. Anyways, then these are special cases for like allocation functions, because allocation functions are really common and also just really nice to have fast. You can always fall back to having to be, assuming it's less conservative. Then what happens is if we don't have any of the allocation or other special cases, then what we do is we look at all instructions that could potentially, be users of that data, and see if, there is a load or a store in an active way to it, which is why aliasing information is really useful. Because if there's aliasing information, it can say, oh, it doesn't hit that, and that's why you see all these aliasing calls. Similarly, if we know that the result is a new allocation, so like, the result of a malloc style thing, as opposed to like, an offset into an existing location, then we can also be more aggressive. And that's why here we have the cases of like, like if it's a new allocation, we only need to check all subsequent instructions to it, versus if it's a pointer that could be an offset into a previous pointer that could have existed from beforehand, we have to check all instructions in there. Because, if this pointer is an offset to a previous pointer, even though we just created the pointer now, the same pointer or the same memory location could have been overwritten or stored actively into by a previous instruction. And basically here, what we're doing is we're looking for all those things to say, could you potentially actively store it? Could you potentially actively load it? And also, could you store into it at all? And then after we've looked at all those instructions that could matter, then basically, if there is an active load and store, okay, sorry, then we're going to assume that it's active and then mark which were the active loads and stores to be able to reevaluate in case they become inactive later. If there isn't an active load and store, it still, however, could be active if we were somehow given it or returning it, right? Because if we have a double star that we allocate and we store memory into it that's active and we return it, we never loaded from it, so then we're actually fine, there's no active load. But because we're returning it or storing it in somewhere to be returned, hence or equivalently captured, then someone after this individual function could load from it. So we need to be cognizant of that case, and vice versa in the other direction. Even if we never store into it, but we only load from it in a potentially active way, if we got this pointer from somewhere else, like from an argument as an example, someone beforehand could have stored active data into it, and thus we have to presume. Hence the sets of cases is like, now that we know that there's no active load and store pair in this function, the only way to facilitate a transfer of active information if it's done at least partially outside of the function, which, as the cases allude to, case A is like either there's a loader store outside before it's called, or like there's a loader store after it's called. In the first case, it can happen if it came from an active global or an argument, or is loaded otherwise from active memory. In other words, like assess the upchain there. And then case B happens if the memory is used as part of an active return or captured, aka stored somewhere in a way that's accessible outside. And then the basic gist is like, now that we've done all of these sort of analyses to see where it came from and if it's potentially actively loaded or not, and then like, if it came from someplace in an active way, it is returned somewhere in an active way, assume it's active, like outside of the function. If it came from somewhere outside of the function, active, and we load it, it's active. If it came from somewhere outside of active and we store into it, because the weird pointer case, as alluded to here, assume active. If we store into it and it's loaded, that's a much more obvious active, but still applicable one. And then also if it's used more generally, and technically means that this case isn't necessary, but like it's written in a way where I understood it as writing it more generally. If we have an active use of it outside, it has to be active to be able to ensure that differential shadows are created. And the basic gist there is if you have a malloc, right? Even if it's never stored into, we still need to make the shadow malloc, and so on and so forth. So hence, if it's ever active, return, you have to assume that it's active because we might need to create that shadow allocation. Yeah, and then that's the rest of pointer land. That's the hardest part of all these analyses. Constant instruction is very easy. It's basically, now you have stores, now you have, loads, and you have the other sort of things. If you're storing integers, great. That's not an active store, even though a store to active memory, may have had to assumed that it was active, but if you're only storing integers to active memory, that's still inactive. And you sort of get the point, and other sort of, optimization simplifications with the same up-down things as before, except now talking about the instruction rather than the value. And it's way shorter, like we already went through the entire definition, because all the harder part is in those other pieces. And yeah, as I alluded to earlier, because Jacob and Martin, I mentioned this, we took the implementation. I'm going to clear the screen here for a second. We took the activity analysis, at least as of whenever we did this ago, and forked it inside of the MLIR one to create, and again, you're going to have to forgive my ignorance of where this ended up. I'm going to assume that it's inside of here. Where did it go? It was somewhere.
I think I did see a PR that didn't get merged.
There's one that didn't get merged, and there's one that did get merged.
Okay.
The one that didn't get merged was a modification on the other one, because it's used inside of the forward mode stuff. Or maybe it didn't get merged. I just did a very simple assumption. Yeah, okay, here's the example. It's inside of M gradient utils reverse, as opposed to its own separate activity, and I'll analyze it. Oh, no, I guess then it didn't get merged. Well, there's a PR then. Oh yeah, this is it. That ports activity analysis as of this time into MLIR, which basically takes the existing activity analysis and replaces most of the, and you can see why I say it's literally a fork. It is literally the same code, because we started with the same code and commented out things to be able to make it MLIR applicable, which we should really merge because it really fixed a bunch of forward mode stuff. And we had commented out stuff that we needed to finish later. The basic gist is that now you have like for all results, because LLVM has only one result, and similar sort of things. So if you actually look here, most of the all ofs are actually done correctly. Yeah. Sorry, this is very specific just to, as a comment to Jacob and Martin, but this is very, very applicable. My suggestion, by the way, would remain, we should get something like this merged quickly and then fuse it into the existing activity analysis to just have a like for all users or for all operands, which for LLVM would be the one result, and for MLIR would be for the all results, and trying to template it to have the two things together. Also, hopefully this explains my earlier comment about the like, it would be really nice to share infrastructure between the two, because this, as an example, is a true fork of the other one. Yeah. Anyways, that is the MLAR specific side. Does that make sense for the MLAR oriented folks?
Could you maybe go over anything you kind of had in mind as to how we will get this merge to happen? I think there are parts of it that are still unclear.
Yeah, I think basically the gist is so again, this is why I say the way to do this is to start by basically as here, forking it, getting it to work separately on its own, because that allows us to figure out all the pieces that will be different, like, you know, LLVM instructions, versions of like weird hard-coded operation lists. Then for those pieces, we're going to need to like abstract it out to a pseudo interface, where that interface for the LLVM level is the same is an instruction, for the MLAR interface is a interface check. And then you would have here a like, you know, the equivalent of a functional, or you can make like a templated for all users, or a for all operands, that then here would do for all results, you know, of this guy, and it would literally call all of i.get results. And then for the LLVM one, the for all results would just call it with the one result. If that makes sense. So like I would suggest by basically first getting an entirely forked version to be completely happy, and then each individual sub piece starts to reuse itself until there is only one. Where the way it starts to reuse itself is by creating like templates over MLAR version, do this, LLVM version, do that. And then most of the implementation will still be in the meat, but then it will call the you know, per specified one as requisite. If that makes sense. It's still, to be clear, going to be somewhat tricky. But the benefit of doing so is that then every single LLVM test is also a test for the MLAR activity analysis. And that is a very, very big benefit to have, and vice versa.
Okay. You mentioned as well that so it's started to get out of sync now, as there have been continual updates and bug fixes to the LLVM activity analysis.
So this PR has not changed as time has moved on, is basically the gist. Which may mean we might want to refocus that. Or start from scratch using exactly, here's all the like how to properly do all ofs, which took Alex and I on a call together figuring out successfully. And then we did figure it out, which is good, but figuring it out took like the correct way to write at the MLIR level, the like combined get all of the blank, and this is the specific blank we need, took us on a call for several hours. Hence the like, oh, get all potential incoming values. This is a very, very non-trivial thing, but that's how you properly do all the like the fee input operand stuff. And as you can see here, this function itself is a helper function that is equivalent to get fee incoming values, which is now just a lot more tricky, but now it exists. And that's why like this example function would be this crazy thing for MLAR, and for LLVM would just be, oh, iterate through all the fee incomings. Great. So we have all the infrastructure. We just need to like, no, do the thing. If that makes sense.
Okay.
But yeah, the fact that like get all the incoming values for a fee node in MLAR block argument land is so complicated is why, as you can see from this definition, is really easy in LLVM, right? Because that's literally just a call to a method. Here, it's a whole shenanigans. Because if we need to find all the operands to something, then we need to look at all the incoming things of something. And thus, this is why it became harder. Now knowing how activity analysis works, like the up-down and the operand user. So that's why we need that. And there's more stuff like that, but it's in this PR. Anyways. So yeah, my first suggestion would probably be rebase this, get this merged. Then start to siphon off stuff. And similarly, like you see this like may allocate memory, may read from memory. You can easily like have this as a template sort of high level thing. And then the may allocate memory is just the equivalent to the LVM, check. And then same with the may read and may write, which is exactly because they replaced the LVM check in the original code. So these are those equivalent of the little things.
Okay. Would you want to get this PR merged as is as soon as possible?
I think it would at minimum be a probably good starting point. It also incidentally fixes other bugs, which there are now tests for inside of this PR, which earlier were not happy, which is good.
Oh, interesting.
Yeah.
So
like,
their file
otherwise, like,
check.
yeah. Having actual MLR test that now works good.
Is there do you have an analogous activity analysis printer?
No, but we should add one. There is inside of LLVM. So if you look inside of if you look inside of the test for LLVM land, and you look at, so we have it also for type analysis, to be clear. You have the ability to print the results and validate that the analysis does what you expect. And it prints the instruction, the type tree. Here, this is the input arguments that it started with. So the return and then the arguments and any constant values known, and then the final end deduced state. You also have that for activity analysis, which is an example here, prints like ICV is constant value, ICI is constant instruction. And given the initial, and return settings, activities. And here you just say, print activity analysis runs an activity analysis function. Activity analysis function to be analyzed, and we have a magic extra guy here called just assume that the arguments are inactive, because sometimes you want that, other times you want to default we assume that they're active. So the default is assume active, with this flag is assume inactive. You get all the fancy activity results.
Right. And I saw that there are also different flags. Like there is, instead of print activity analysis, there is enzyme print activity.
Yes, so that is a flag that will, so this print activity analysis is basically just the special optimization pass that just runs activity analysis and prints the results. Enzyme print activity, if you look at the definition of activity analysis, if we go back to, do I have somewhere where that exists? Sure, close enough here. Enzyme print activity will just at all points inside of activity analysis, you'll see, like, if printing say, oh, this is constant instruction because X, this is an active instruction because X, and it will just, for every decision it makes, tell you what it did and why. Because otherwise figuring out why is really hard. This is also why if you turn it on, it might make a really big log, especially if you have a lot of instructions. But having it is really useful because then you can see why the things happen and try to like deduce that from a trace, which might be otherwise difficult to have. And there's a similar flag also for type analysis, enzyme print type. And you can even do enzyme print type and the print activity analysis. So it will, rather than running the enzyme pass, run the activity analysis printer pass, and then also print the inside internal results as it's running this pass. You can also just run print activity analysis and stuff like this inside of the Enzyme Explorer. Thanks to Tim. Yeah, there's also other analyses and stuff too, but I do need to go at one point, so we can have other analysis conversations a different day, like differential use analysis, all of the fun things. But these I think were the big ones that I thought were the foundational internals, which you should really write a paper about one day. So if anyone is very enterprising, wants to take this entire discussion and decide to put it in a LaTeX doc for us to submit as a PL how things work, definitely would be a great thing for us to do. Hasn't been sufficiently priority yet.
And just to briefly recap, or to step back for a second, is the important public interface of activity analysis the two functions is constant value and is constant instruction?
Yes.
Cool.
And that is what everything else builds off of. And MLR land, we could rename it is constant operation, but you get the point. Other questions? This either means that I did a really good job of just blabbering on for 2 hours, or I did a really bad job of blabbering on for 2 hours, that there aren't more questions. So, but we have a recording at least, hopefully, somewhere. Other question, comment, things?
Yeah, I think this has been incredibly helpful. Thank you very much. I think at this point, it will require some deep diving now with additional context to make everything more concrete.
That is fair. And also, as alluded to in the weekly meeting the other day, if anyone wants to help write up all the things that were not documented or even could be better documented, maybe in a form of anything, website, blog post, real MVP. Also, Tim, hopefully that also answers some other lingering questions of what you and I were talking about regarding type analysis stuff.
Yeah, it does. Yeah, I should probably at some point do the try stuff finally. But yeah, we'll see.
Is fair. Any other comment things? Okay, in which case I'm going to stop the recording. As soon as I figure out how to do that.